And we are live. Okay, welcome everyone. Welcome to the SciGeeks podcast. And so, as you can see today with us is Dario here. So, welcome, Dario. Dario works at Clastics. So, can you just introduce briefly yourself before we go into a teaser of today's episode?
Yeah, I'll try. So my name is Dario Tranchitella. The surname is always a mess, especially with Americans. After 3 years, some of my colleagues they discovered that it was Tranchitella instead of Tranchitella, and most of the time I spend the time creating memes on LinkedIn, on Twitter. Now it's not anymore Twitter, but you're getting the point. And as a part-time job, I write code. I co-founded Classics in 2020, and I focus on Kubernetes mostly, on the multi-tenancy, and I've been a software engineer turned DevOps engineer, site-reliability engineer, back and forth. So essentially, I write code, mostly Go, about Kubernetes stuff, and that's all.
Yeah, cool. So just to let you know that Ciangotini is not easier to say in English than than Tranquitella, so you're
We're
not
sharing
alone.
the same pain, you know.
Yeah. Uh, cool. So let me go directly to the point. I like to share a teaser that is the result of some interaction we had in the past where we set up some cool stuff that I want to discuss with you today. So let's dive in directly into the terminal, and you can see here we have a Kubernetes cluster that get as two physical nodes. So get node. There are two physical nodes and a node that is not really physical. You can see already from the version that is not something that is running natively on a node, and it's called Kubernetes GPU. Can you just introduce briefly, Dario, what K's GPU is?
I know that bad guy. So
Yeah.
so essentially, Case GPU is a solution that we developed together with CWeb. CWeb is a cloud provider from Italy, and they started a huge investment. They started investing in GPUs, so you can reserve instances as virtual machines consuming the GPUs, or you can start with this serverless solution. So the idea here is to simplify the infrastructure setup and the provisioning and deprovisioning of GPUs, mostly about Kubernetes. So the use case is that maybe you're running on-prem, and we all know that right now GPUs are like gold; they're very, very expensive. So maybe you don't have enough money to buy your own, and we've been used to the cloud where you can spin up virtual machines or whatever you want in a matter of seconds. So we try to create the same experience that we're expecting from the cloud about resources, but for GPUs. But of course, the GPUs, they must be in the same data center or in the same cloud environment where your Kubernetes cluster is running. So Case GPU is an implementation of a virtual kubelet, but I don't want to spoil so much because, Diego,
Yeah.
you know better than me the virtual kubelets. Remember,
No,
we talk a lot.
I'm not sure about that, but yeah, we are talking the same language there. So yeah, just for the moment, this is a virtual node. All right, guys. So
it's a virtual node.
and what is cool about this virtual node is that if I do get pod -n Helix, that is the next tool we are talking about. All right, there is a pod here called runner Helix runner that now it would be awful to put it wide. Well, let me check. Yeah, definitely awful. But trust me, you see here a pod, follow the line, and you see that eventually is running in Case GPU node. Okay? So this guy here is the responsible for the magic that I'm just about to show you. All right. The other components are components that are running on physical nodes. So any Kubernetes cluster, any even single machine with Docker Compose can bring up a portal like the one I'm going to show. So this is Eli AI work and tool. So I will put all the references also in the chat probably. So let me quickly, very quickly, let you some information live. Okay, and so you install your stuff and you end up on this page. This page that is very similar to a chat GPT at your end, if you wish. So you have new session where you can ask for text generation or image generation, but you have also much more. So you can deploy the so-called runner that are daemon connecting to this hub, able to run generative AI inference on remote host. So if you start to connect the dots here, you start thinking that this remote host here called runner Helix runner is, by accident or not, the same guy that is running on the remote host on CWeb. So what this means that if I do something like this, now I ask, hey, can you say hello to our SciGeeks friends? Oops. This is running on the remote host on the virtual node. All right, so it was very quick. Helix has already implementation for different kind of stuff that are not only inference, are the so-called applications. So you can store application that you can integrate with each other, but yeah, save this for later, and also fine-tuning and RAG. So a complete platform for generative AI application development. We decided in this episode to merge the two things because they look cool and can be also very convenient. What do you think, Dario? It was fast and clear enough. You want to add anything?
No, absolutely. It's mesmerizing. I will say that also the fact that it's running in Kubernetes, it's very cool because I'm using Kubernetes since some years. I don't remember anymore, but essentially what I like to describe Kubernetes is that it's a de facto standard. We're Italians, so we're using a lot of Latinism, but it means that it can run everywhere. So it can run on your machine, on the cloud, on-prem, even for GPUs. And combining the two solutions together, essentially you're creating a software stack, I will say, even though we have GPUs, so we have hardware, but essentially it's portable, so it can run everywhere. And the idea behind Kate's GPU was to take full advantage of Kubernetes because we're already running everything on Kubernetes. So what's going to happen if I don't have enough GPUs, or maybe because they are too much expensive, I can run them maybe even just a matter of seconds. It's up to you because containers are running inside of Kubernetes. And long story short, essentially, it can run everywhere. So today, they are running on CWeb. Tomorrow, they can run on-prem. They can run on hyperscalers or cloud, and so on and so forth. So it's very, very cool.
Yeah, and some that follows this channel also know that can run on Slarm as well somehow. So that would be cool as well. And yeah, I want one question for you right away, and it's about how this magic works without going to the very fine details, of course, but that you probably even couldn't
Okay,
do. So,
okay. So it's going to be something like explain me virtual kubelets like I'm 5 years old. Pretty complicated, but no, it's pretty straightforward. So keep in mind that Kubernetes is a sort of framework to create distributed computing platforms. So it means that we have the control planes and then we have the worker nodes. The control plane is the one that is hosting the data. So we have all the pods, the deployments, the secrets, the config map, but we are running our workloads on the worker nodes. So this separation is pretty important here because the worker nodes are essentially cattle. So they could be virtual machines, they could be bare metal instances, they can be whatever you want. And how this hardware can be assigned to a Kubernetes cluster, to a Kubernetes control plane. Essentially, we have the kubelet. Originally, it was named Minion. I always thought that Minion was coming from Despicable Me, but I'm not so sure about that. Who knows? Anyway, the kubelet is the one that is interacting directly with the control plane. And yeah, the design that you're putting here as a chart is perfect. So the kubelet is registering to the Kubernetes control plane, and essentially is going to be a sort of bridge, a sort of an adapter. So it announced itself saying, I have this CPU, this amount of memory, of storage, ephemeral storage, and so on and so forth. So every time we have a node and we would like to deploy our applications into the nodes, in Kubernetes, we are creating some pods. And these pods then are assigned to the kubelet according to some algorithm. So there is a scheduler, but it's going to be too much complicated. You just need to think about that we have the kubelets. So the kubelets are the ones that are saying, I have resources that you can consume, and we can have multiple resources. I always said memory and CPU, but if we think about GPU, since we're talking about GPUs here, you can announce also GPUs. And what we did essentially was to say, let's imagine I have GPUs and I would like to make them consumable from the outside. So there is a nice project that is named Virtual Kubelet, and it means that a component running inside of your Kubernetes cluster, and it says, I'm a virtual kubelet, I have a signature. So it means that the kubelet is interacting with me using a contract, an API contract, and I return the list of the workloads. So essentially keep in mind that in Kubernetes, everything is based on contracts. In the end, Kubernetes is a software, and we all know that when we are writing software, we have interfaces, we have contracts, we have scheme, and so on and so forth. So essentially, it's the same thing here. So the virtual kubelet expose the same methods, or rather, they are not methods, but they are HTTP with payloads and so on and so forth, compared to a regular kubelet. And what is doing this virtual kubelet? It's up to you. There are plenty of implementations. The virtual kubelet is just a contract, and it's up to the implementation to define what we would like to offer. So it means that every time we have a pod assigned to the virtual kubelet, our implementation can start a virtual machine. You can start a resource, something externally. The example here could be even a Slarm instance. Slarm or Slurm? Maybe it's Slarm.
Yeah, maybe
I know.
Slarm, yeah.
I don't know. I know. SLURM. I don't know. So
Yeah.
it's up to you. Acronyms are always challenging for me. I'm not a native speaker. That's the reason. So essentially, with the virtual kubelet, what we did with Kate's GPU was saying we would like to start some pods running on top of GPUs. And we can talk later about the concept of GPUs. You just need to think about here that with the virtual kubelet, you can extend the deployments of something that is represented as a pod. So it's entirely managed by Kubernetes, but it represents something that is different compared to a pod. It could be a remote container, it could be a Cloud Run instance, it could be a virtual machine, it could be a Slarm. It's up to you. So essentially, it's very interesting because it allows to extend also the topology of a Kubernetes cluster and to manage resources that are not directly related to Kubernetes.
Yeah, and in doing that, I think the cool thing here is that you can also foresee a way for the control plane for the user, if you want, or for the APIs to say and to tell additional information to Virtual Kubelet about a pod. So that in other cases would be ignored, but I don't know, I think about annotations that we use for the Slurm implementation. You can pass whatever information that is typical for that backend here, for that custom implementation, both from the internals of Kubernetes, but also from the user perspective. So that's the flexibility of this tool.
Yeah, absolutely.
And okay, so in this particular case, so when running at CWeb, how the resource management, how we end up using a GPU on this right-hand side of the plot.
Okay, so
Holy cow, let me, please, people in chat, let me know that you're not seeing the drawing. So okay, now it's fine.
Okay, that's great. So it's my turn right now. So essentially, keep in mind that we have our node that is a virtual cube. Well, it's a kubelet per se, and then we have the virtual kubelet. So it means that this is K's GPU, and we are announcing some CPU, memory, and GPUs. So I'll try to keep it simple. It's way much complicated rather than this one. But essentially, we are running in a Kubernetes cluster that is a multi-tenant aware. So what is multi-tenancy? So the multi-tenancy in Kubernetes is something that we are already used to because we have the namespaces. So the namespaces are a way to separate in a logic way the workloads. You can imagine I have dev, QA, and production. Of course, that's a silly example because I will run the production cluster, well, the production workloads in the same environment where I have also development. But you're getting the point.
Yeah.
So to make it more production grade, you can think that maybe I'm a huge bank, I'm a huge organization, I have multiple development teams, and essentially each team has its own space. So it's a sort of slicing the Kubernetes cluster into groups, and in these groups, I can assign quotas. I can essentially, it's a sort of slice, okay, a partition of a NARD disk, but compared to Kubernetes. So in the multi-tenancy, this is pretty simple. You can do with namespaces, but the problem is that it's going to be very, very challenging when you have hostile tenants. So the concept of tenant, it's like users, regular users. If they're part of, say, organization, it's pretty easy.
Yeah.
We are all friends and we're happy to be together. It could be challenging if they're from different organizations or even from organizations that don't know each other. So essentially, we have a multi-tenant environment here, and we have a bunch of nodes. So I'm going to create the GPU nodes, GPU node, and these GPU nodes are available to consumption. But the problem is it's way more complicated because it's not just a matter of CPU. In Kubernetes, you just declare CPU, memory, end of the story, but maybe this could be a different color, let's say orange, because this is an A100, sorry. Then we have these blue ones, and we're talking about H100, and maybe these ones, let's go for the green, they are L40. Okay, so we have a topology here. So how can we expose this topology to end users? Because they don't have visibility. The idea of the serverless approach is pretty simple because I don't want to manage infrastructure. Every serverless solution, it says straightforward, you don't need to take care of the provisioning, and so on and so forth. So with the virtual kubelet, essentially, that is running not directly here. So we are going to move this guy here in our cluster. We are connecting to the CWeb cluster, where we have the multi-tenancy, and our black magic, I will say that it's assigning the pods of each user to the available GPU node here, ensuring that there is quality of service, we are not creating noisy neighbor effects, and so on and so forth. And how we are doing that? Essentially, we have the implementation of the virtual kubelet, but we are also using some other tools like Capsule. By the way, it has been my first open source project, and now it's part of the CNC app. And we are using also Kamaji, that is my last open source project as classics, of course, that is doing something that is named controlplane as a service. Just to keep it short, essentially, what we need to do is to say, we want to expose these kind of instances. So instead of creating multiple virtual kubelet, because it would be virtual kubelet for H100, or maybe virtual kubelet then for, I don't know, A100, it would be too much complicated. What we went was a simple and straightforward implementation like this, and we are installing automatically some additional runtime classes. So in Kubernetes, the runtime class is a concept that we use to define a different workload. So if you think about containers, you have container D, that essentially it's run C, or you can have a different runtime class, maybe because you're using GPUs. Because
Yeah.
with the GPUs, I'm not very the right guy here trying to explain, but there is a sort of hook system with NVIDIA drivers. So essentially, you're spinning up a runC container, you create a connection to the assigned GPU, and essentially you are connected to the CUDA drivers of the device, and then you have a sort of privileged PCI connection with the card. It's way more complicated, but just to make it simple.
So
Also,
just one comment. So it's correct to say that this runtime class is the tag that you use
yeah.
to define all the following flow until the green, blue, or
Yes,
yellow boxes.
we are using these ones. So you will have CWeb 800
Yeah.
or CWeb 800. So it means that what you need to do is to say, this is a pod. I want to assign that with the virtual kubelet using one of these classes. And then what we are doing is just a replication. So we are copying back and forth our pod from the origin cluster to the remote cluster. So this pod will be here replicated. So it's going to be a different color. Oops, let's say blue, and this way. I'm not very good at Excalibur, my bad. And this pod is going to be assigned to one of these nodes, and essentially what we have here is a sort of bridge. So our pod in our user space cluster is essentially replicated in a multi-tenant environment here, where essentially it's running as a pod. So I don't need to translate like a virtual machine. They are the same context. So I can do an exec, I can do a port forward, I can retrieve the logs, and so on and so forth. And it's
Yeah.
very convenient because you don't need to change anything from the user space. It's just a matter of runtime class. Once you assign the runtime class, automatically can be assigned to the virtual kubelet, and it runs as you show before, essentially.
So let me. Oops. Just wanted to show this in practice. So I might have here exactly the pod that we showed before. So this is the runner that is following exactly all this route down here. And as you can see, let me check.
Line 28.
Okay. Right. 28.
Yeah, you're
Okay.
using the, yeah. No, but it was 28
28 down.
down. Yeah.
Now it's still 28. Okay, let me search for
Runtime
runtime. It's
plus
better.
8.
Yeah. Okay, so I found that. Okay. Here we are. So this is the runtime class name. And essentially then the other stuff is that you want to explicitly select that node probably. So you have here some node selector and toleration. Well, the toleration, I suppose that is the same also for interlink, is to avoid that something that shouldn't go there end up on a GPU node where it doesn't belong to.
Keep in mind that you can simplify here because you can avoid the node selector and the tolerations. Because if you try to take
because
a
of
look
the run class,
yeah, in the runtime class,
Yeah.
there is a key. I don't remember anymore. I remember the name, but essentially you can force the node selector and the toleration, so you don't need to type that every time. So it's just a matter of assigning the runtime class.
Yeah, cool. Right. Okay. So here there are the resource limit and request that these are needed instead, right? Because I suppose that you can have multiple containers, but only one of them should use GPUs.
Keep in mind that we are mostly doing with CWeb. We are just operating GPUs, so
Okay.
you can skip assigning the limits. Automatically, what we do is, since it's a serverless platform, we are automatically assigning the amount of GPUs, the memory, and CPU. I was saying GPU, but I already said that. So you can avoid that. But if you want, I don't know, maybe because you have a multi-container application,
Yeah.
because in the pod you can run multiple
Yeah,
containers,
that's the point.
you can create a sort of partition of memory. So it's up to you. Of course, what's going to happen if you put memory something like 1 TB? It's not going to work because we don't have a proper hardware underlying infrastructure. But the approach here is to make it very, very smooth. So you can totally forget about the limits. We are automatically assigning that. So if you try also to run the list, if you try to enumerate the memory inside of the container, you will notice that you're consuming all the available memory there.
Okay, and if I put another container in here, when I specify no NVIDIA GPU, what happened? The whole pod is
Well,
consuming just one GPU, right?
one GPU. It
Okay.
depends, mostly because sharing memory with GPUs is very challenging. Also because we had a CVE yesterday. It has been published a CVE about the NVIDIA Container Runtime Toolkit. No, NVIDIA Container Toolkit. We're just talking about NVIDIA's because the MD ROC is totally a different approach. Anyway, with CWeb, what we're doing is that we are shaping the infrastructure according to the customer's inputs. So it means that if you're running an H100, it means that pretty sure you want a sizable amount of resources. So we are always doing a sort of virtualization here. It's a sort of secret sauce that we are doing. So essentially, we are ending up with a lot of nodes, but a few pods. So it's going to have the same concept of creating a virtual machine. But what we are doing here is that with Kubernetes, we can automate all the joining process. It's going to be much quicker. And also we have a abstraction layer. It's not a proper abstraction, but it works everywhere. So that's the main concept. And what we were looking for was also to create an experience that was provisioning very, very fast. So essentially we have a pool and you can spin up GPU instances in a matter of seconds. So you don't need to create the virtual machine, wait for the IP, then the SSH, install everything. We are doing everything behind the curtains, and we are just waiting for the user workloads. So essentially, the concept of serverless, actually.
Yeah, cool. And so, in terms of isolation, before going a bit further and see some of the use cases for this kind of on-demand needs, do you have use cases that are kind of confidential training or something like that? So that request, for instance, in sciences, you can ask for entire dedicated node to avoid that kind of security risk that you mentioned before.
Well, keep in mind that there is a project that is confidential computing, confidential containers. I saw also a presentation from KubeCon, and it's very, very interesting. And right now, we are not offering such a service. But CWeb, keep in mind that if you're looking just for your private cluster, it can be offered. It's not a big problem. The issues here is that there are multiple surfaces here. We have Kubernetes, where we have the multi-tenancy, and then we have a segregation at the namespace level, where we apply a set of policies like the network, the limit, the container limits, the resource quota, and also we do our best according to the multi-tenancy benchmark guidelines to prevent privilege escalation. So it means that even though the pod is able to escape, it's not CH root, but it escapes from its process, from its jailing. We have just a few pods running in the same virtual machine. So it means that we are not mixing multi-tenant workloads together. So just to offer a high segregation between the workloads. Otherwise, it could be very, very, very bad. But I was also thinking about the problems with networking because from the Linux standpoint, CPU, memory, it's pretty easy to manage that. We have the namespaces, we have the C groups. For the network is way more challenging. I'm not saying that it's impossible, but it requires more efforts, even though we are working on that.
Yeah, nice. Okay. Yeah, I just made the question because we start discussing, also in scientific endeavors, how to manage them. So I was just curious. And yeah, if it's okay for you, I go through a use case that is possible to satisfy with a combination of Helix and C-Web plus Kate's GPU. And one thing is that before going ahead, you see here that we also have the memory that is corresponding to the one that we requested into the pod. So everything works as expected. I also wanted to share that when we say that it's a real pod with no exception, if I do kubectl logs for that pod, I should have, at least before it was working, I should have the complete log of all the download of the models and so on and so forth. So you can really experience a real node without having it into your cluster. And this will allow you to do some fancy stuff. Fancy stuff that, thanks to the architecture of Helix, are really a perfect match with this design, because the idea of the portal that I'm showing you, that is Helix AML, if you want to look for the URL, it's this one. So here on the physical node you have a pod, but this time, you have a pod, but this time this is your hub, if you want, your Helix hub, that is exposing a web interface. Here there is a REST interface of some sort, and this is technically where the magic happens, because you want your remote pod here, like I copy and paste. Let's say now we are on the 100, so just to be precise, this is our pod right now. Here there is the so-called runner, okay? And what does the runner do is this nice thing. You might have heard runner terminology. If you use GitLab, for instance, there are runners that works pretty much the same. So some daemons, some instances that are executing some code that are waiting for work to come from the central hub, okay? And to do that, they do not need any open port, anything. They connect back to the endpoint of the app. And if there is anyone from Helix connected, please comment with correction if I'm saying something stupid. But I'm quite sure this is working because the demo is working. So it's connecting back without the need to open any port from the remote part. And it's listening for work to be executed. And the work to be executed in this case are prompt to be satisfied by GenAI inference. So you see here why I say that this is a perfect match, because you want to have something very generic on the left-hand side that runs on the cloud-specific task, like a web service exposed to the users. And then you want something that is hidden to the user, so that actually does the heavy duty here. And this is the runner. For the runner, you have one desiderata, and you do not want to open any network port, introduce any requirement from the network perspective on the right-hand side. And in this design, the Helix implementation is very cool. I find this very useful. And so with this idea in mind, you can spawn whenever number of runner on this virtual node, on another virtual node if you have any other cloud provider out there. So it's very flexible and it runs pretty much everywhere you can run a container.
You know, Diego,
Yeah.
I'm just joking also because my main duty, day duty, is crafting memes and doing a lot of dank jokes or dad jokes. And if you think about right now, there is also a trend that is the cloud repatriation. So it means that a lot of organizations are leaving the cloud and moving back to the on-prem or private cloud. And it's something that I was joking yesterday also with Adriano, that is the founder of Classics. So it's back to the future. And if you think about this, it's pretty similar also to the RPC calls that we used a long time ago with AES 400. So we have the remote procedural calls. Right now, we are more used about gRPCs, but it's pretty similar, the architecture. So it's back to the future again.
Yeah, yeah, pretty interesting. Yes, exactly. Um, the scenario changed, but it converged back to to the
Or
past. So,
I
yeah,
know it, they are
yeah,
totally
yeah, no,
different,
no.
but it's the architecture is pretty similar because essentially you don't need anymore. You just need a terminal or something that is running your machine, and everything is offloaded somewhere else that you're not taking care anymore.
Yeah, cool. So if there are any questions on chat, I give you some time to write there. While I'm preparing for a quick demo of what you can do with application on a Helix, and now we can use this A100 that we have in a improper way, I think. No, let's say just for the demo, and then since it's taking longer to do fine tune of any model, it's not matter of this, but I let you the links to the documentation. And the idea is that you can pass whatever kind of information to fine tune your models, and also to recover additional information on the fly. So this line here is very cool, but it's not going to be shown in this episode. While I found an example of this application pretty useful. And yeah, no, I spoiled it, sorry. App Store. No, I want to create a new app, sorry. Okay, so I have one already created, but let's create another one. The idea here is that you have this app, this runner that executes whatever you ask for, and then you can start playing with different prompts to create your own agent, if you want. It's not really the proper time in this case, probably, but yeah, your own function that can do fancy stuff. So here you see a serious example that I tried, that is transform any pod I pass you into any set of pod or Kubernetes manifest I pass you into an Helm chart with some values. And or this is the one that we are going to do is pirate 2 and say, okay, talk, the typical talk like a pirate. And then here you can pass the instructions. So you are a pirate that loves silly jokes. Okay? And yeah, that's all. You give a name, instruction for his behavior, and you can model the behavior of your endpoint, of your application, in whatever way you want. So you can test this beforehand, and so you say, hi, how are you? And this will actually answer like a pirate, and yeah, so, but the cool thing is that you have then API keys to ask, to use prompt to this kind of endpoint from outside, also from inside if you want. So you have an app catalog here where you can select different application, and you can do fancy stuff already also here. So it's a prompt like all the others, but it's using a custom implementation. This works for image, text, and whatever. One more thing that I want to let you know, because it's interesting, is that there is a native API integration for the application, but there is also a GPT script kind of runner on server. And this is pretty more advanced and out of scope for this episode, but we will talk about GPT script in the next episodes. So stay tuned. This is kind of a bash script for AI, where you can pass all the steps, make tools, cooperate, and it's pretty fun. So yeah, you have everything in one place, on the cloud, and the only thing that you offload to the outside is the GPU that are you using on demand on CWeb. So I don't know, Dario, you want to try some up or?
I was really impressed about the parrot talking, so it's very, very impressive. I was wondering, do we really need all the AI machine learning stuff or serious stuff if we can just have parrots talking to us? I mean,
yeah, we can also ask pirates if he knows virtual nodes, probably.
yeah, maybe we could ask about ghost ships.
Yeah, right. So, okay, one question that I have since the beginning, and I don't know if you have a complete answer. I doubt that anyone has a complete answer to this, but what is the roadmap that you see for this kind of technology or this kind of solution from your perspective, so from Classic's perspective?
Oh, well, it's going to be a bit opinionated because we have a roadmap we are sharing with CWeb. So keep in mind that CWeb is the infrastructure provider, and they are working with us as Classics, where we are combining our technology. So we started with the 1.1 edition, 1.1 version. Then in 1.2, we allow the availability to create custom endpoints. So essentially, I have something. In this example, it's pretty neat because Helix is doing all the dull job for you. But if you want to create from scratch, you need to expose those workloads. And we implemented a way to get endpoints, private endpoints or public endpoints with TLS certificates directly from CWeb. So you don't need to mangle with kubectl port forward. It's going to work, but sometimes it's much easier having a service with a fully qualified domain name where you can reach out to your application. So this has been implemented in V1.2, and we have V1.3, and it must be released before the end of this current month. And I'm actively working on that during the nights. Just joking. I'm always working because my main job is creating memes. But we are going to provide also support for storage because storage is very, very complicated. As you can imagine, we are downloading a lot of data. And since we are running as pods, it means that we don't have a proper instance. So the benefit of a solution like Case GPU is that you can scale up and scale down. So when you're scaling down, of course, you're losing all the data, all the runtime data. And if you're scaling up because maybe you have a request or something like that, or maybe because you need to restart the training of your model, you cannot download everything back. So with CWeb, essentially, we are working also with a nice storage vendor that is named Bus Data. And essentially, what you need to do is, like regular Kubernetes clusters, you need to create a persistent volume claim. That persistent volume claim will be automatically assigned to the CWeb infrastructure, and you get the storage. And the storage there is mesmerizing. I mean, you can increase that as many gigabytes of terabytes you want. So it's something that it's very it's incredible because essentially you pay not for the reservation but for the effective data you're storing. So you can have a request for 3 gigabytes, but if you have 0 bytes, you pay 0. So that's the very concept of serverless. So we are moving towards in making the infrastructure management for AI, machine learning, or whatever is consuming GPUs for workloads effective and easy to manage. So simplifying the infrastructure.
All right. So and
this is the answer from the product. From the geek standpoint, I would like to see more implementations about virtual kubelets. I know that you're also a big fan of virtual kubelets, and that's the reason also because we met.
Yeah.
Um, and I think that right now we need to work with the community trying to demystifying virtual kubelets because they can help a lot. I would like also to do a sort of kudos, a sort of prize also to the LICO team. Example generic, LICO is a project that was from originally from the Politecnico di Torino, Polytechnic University of Turin. And with LICO, essentially, you leverage on the virtual kubelet to create a sort of federation of Kubernetes clusters. That's just a use case of the virtual kubelets. And I think that if we evangelize, if we work with the community, we can find a lot of other use cases that will solve all the dilemmas that we have on Kubernetes. So a prize to the community to work together in finding new solutions.
Yeah, I second this too. I met already, I think, several years ago with one of people from the LICO team, and yeah, it was actually one of the things that convinced me to start looking with more attention to this kind of technology. And definitely, we start to hearing this need also in the science domain. And I was mentioning before the live stream to you that we are struggling really to integrate our data science framework that are running on Kubernetes into supercomputers where we have access that are running batch system, for instance. And yeah, and this is yet another example where the abstraction of virtual kubelet and the interlink is doing this. In this case, it's helping a lot. It's opening the possibility for users to leverage resources that they couldn't before. So yeah, I think it's time to evangelize a bit. Yes, yes, I agree.
In the end, Kubernetes is a lingua franca, another Latinism,
Yeah.
trying to be Italian, but it's a lingua franca, so it means that it can be a sort of language to develop something that is not just an application or workload. It could be whatever you want with the concept of virtual kubelet.
Yeah, cannot agree more. Yeah, and yeah, so I think I have a lot of other questions, but just one quick one before leave. About quotas implementation, if I go back just, people see someone online want to comment, please do it. Yeah, let me share again. Okay. In the quota, if I want to set a quota from the perspective of the user, so the available resources shown by the virtual kubelet, how are set in the case of case GPU, are static or are synced with some?
No, they are dynamic. So
Okay.
essentially, keep in mind that we don't have quota in CWeb, so
Yeah.
we have unlimited resources. You can spot the lie here, but I'm not joking. I mean, the concept of the cluster here is that we are leveraging on pooling. So it means that we saw a pattern, a bad pattern in the past. So people reserving GPUs, they are leaving it there in idle, maybe assigned to a cluster, but in idle and spending money. Instead, the concept here is pretty similar to what you can have with the carpooling or bike pooling. So you're using the GPU and then you stop your execution, and maybe a few minutes after you stop the execution, another customer is asking for the GPU. So the concept here is that we have this pool where we are doing some sort of proactive monitoring and proactive capacity planning. And the idea here is to say you don't need to wait for minutes. Well, then you know that bad things happen. So sometimes you need to wait some couple of minutes. But in the end, you can consume as many GPUs as you want. There is no limit at all. I mean, what we are asking is that if you're not using the GPU, even though you're paying, you can stop that because you're not going to get lost it. I mean, C-Web is doing a lot of investments on GPUs. So forget about keeping it idle because we are extending the cluster when you need a new GPU.
All right. Yeah. Cool. So I think we have a lot of handle to leave into the description of different channels. So I'll ask you later to pass me all the links that you can imagine. But you people that are listening, yeah, you will find definitely all the link to the documentation site, whatever we mentioned in this episode in the description. Yeah, that's all from my side. I don't know if Dario, you have some final words or.
Well, I'm very happy to be here also because I love science. I'm considering myself as a sort of geek, as we discussed. I'm trying to follow the science, but my background is just about IT. So it was really helpful to be here, meeting you in real life, and also this time again virtually. And thanks so much for the opportunity to present Case GPU.
Yeah, and I renew publicly the invite for you if you want to come to CERN or to some INFM laboratory.
Say no more. I'm already joining.
You're welcome. So. And all right. So, and definitely thank you, Dario, for this really complete overview. I love it, and yeah. Have a nice day, you all, and thank you.